3. What are the intermolecular forces present in each? Okay, we have H2O, He, CH3, Cl, and CO. Okay, so let's first list out the intermolecular forces. We have London dispersion, which is something that everything has. Okay, so right now I'm just going to actually answer that part, and we're going to say all. Okay, we have dipole-dipole. Okay, which is going to be also, well, actually we don't know yet, we're just going to leave it as that. We have sorry, I'm blanking out a little bit. We also have hydrogen bonds. Okay, and as the last one, we kind of just list ionic there, because that does play a role in intermolecular forces. With that being said, though, let's now talk about these. Okay, so let's start with dipole-dipole, because as I said, London dispersion, everything has London dispersion forces. It's like the basic force that just kind of like, if you think of these atoms as planets, when they pass by, they're always kind of exerting that little, I guess, gravitational force towards each other. It's almost negligible, but it is a force included there. Okay, now dipole-dipole bonds specifically refer to your periodic table, your electronegativity. So, with that being said, H2O, okay, we draw like that to show that hydrogen's bond with oxygen. So we want to know the electronegativity difference between hydrogen and oxygen. Okay, so it's going to be electronegativity. Where is that number? 3.44 for oxygen and 2.20 for hydrogen. Okay, so that's going to be 1.24. And if you recall, at least from your notes, the dipole interactions, okay, have a range 0. So anything less than 0.4, that's going to be a non-polar bond. Okay, non-polar covalent bond. Anything between 0.4 to 1.6, that's a polar covalent bond. Okay, and anything greater than 2.0, okay, that's going to be an ionic bond. But more specifically, anything that has a metal and a non-metal bond together is typically going to be in an ionic bond. Okay, and so that range from 1.6 to 2.0, if it's a metal and a non-metal, it counts as ionic bond. But if it's still two non-metals, no matter how big the difference is, it's still going to be considered a polar bond. Okay, so with that being said, H2O 1.24, helium is a molecule by itself, so it literally cannot exert a dipole-dipole because there's no other molecule with it, so this one cannot have that force. CH3Cl, which does look like this, the one we focus on actually is going to be the bond between the carbon and the chlorine, because if you did the carbon and hydrogen, just as a context so you're not a little lost, we have carbon has 2.55 and hydrogen has 2.20. So it is a type of bond still, but it's actually the difference is 0.35. So it's actually a non-polar covalent bond, which is why we don't count it, because that's not going to exert a dipole-dipole interaction, because there's not really any preference the electrons have on which side they want to be on. There's no positive or negative ends. But carbon and chlorine, okay, chlorine has electronegativity of 3.16, and carbon has 2.55. So that's going to be a 0.61 difference, which in these numbers is significant because that means that carbon and chlorine exert enough to where they actually form a dipole-dipole bond, okay? So with that being said, this one checks out, this one checks out, and now carbon-oxygen, okay? Carbon monoxide, we have oxygen has 3.44 minus 2.55. We have 0.89, okay? Something like this. I forget how carbon monoxide will bond. But yes, so with that being said, I'm just gonna write there because I don't know how it bonds. But the difference we know is 0.89, which checks out. So dipole-dipole interactions will be H2O, CH3Cl, and CO. And then hydrogen bonds, this one you have to memorize, unfortunately. There's 3 types, okay? There's hydrogen, there's hydrogen bonded with fluorine, hydrogen bonded with nitrogen, and as you maybe guessed based on your previous notes, hydrogen bonded with oxygen. So water molecules actually are a good example of hydrogen bonds. And looking at the rest, we have no other hydrogen bonds present, okay? So H2O will be the only one with hydrogen bonds. And then ionic bonds, that's when you specifically have a metal and a non-metal. And when you look at all these, everything here listed is a non-metal. So that's none. And the forces go like that, aka hydrogen bonds are, well, ionic bonds are the strongest, but the ones present, the H2O molecule probably the strongest one, and then followed by we can't really say between CH3Cl and CO, but we do know that they do exert dipole-dipole and then London dispersion. So as you can see, typically when you go down to the strength, you would notice that water, if it has hydrogen bonds, it most likely has dipole-dipole, and it obviously has London dispersion because London dispersion is always there. So that is how you would solve that question there. H2O, yep, dipole-dipole interaction, specifically hydrogen bonding, exactly. Helium only has London dispersion force, as we noted. CH3Cl, this is actually going to be a dipole-dipole interaction, not an ion dipole interaction, just because of, like, in terms of, I guess, dissociation, no, you would still have just dipole-dipole interaction. CH3Cl likes to just, even though it forms those ends of positive and negative, the negative being on the chlorine, it's still just going to be dipole-dipole. And carbon monoxide, that one is also dipole-dipole interaction, okay? So let me see here, occurs when an ion encounters a polar molecule. I do not see, in this case, that we're going to be dealing with an ion dipole interaction because of the fact that we don't have any metals. So I'm going to say this is partially correct, but CH3Cl is just going to be dipole-dipole. CH3Cl is just dipole-dipole. Okay? If we were dealing with like NaCl, that would make sense. Or like if they were saying that CH3Cl, if it was poured in like a salt solution, which does have NaCl in it, then it would be experiencing that ion dipole interaction because the ions specifically from sodium would be reacting with the dipoles formed by the CH3Cl. But that would be a lot of assumptions made. It doesn't say any solutions submerged in. So as the molecule interacting with itself, so interacting with other CH3Cls, is just going to be dipole-dipole, okay? So I'm still going to say it's correct because for the rest of them, it does explain it. But this is the type of sheet you're looking for here.